The next speaker for us is Mr. Hasan Muhammed from the University of York of the United Kingdom. Their research focus is on simulating turbulent transport and the instabilities that drive it as a function of divertor geometry.
Cool. Hi everyone, I'm Hasan. I'm going to talk to you about turbulent transport and novel divertor configurations. I'm at the University of York, being supervised by Ben Dudson, also at York, and John Amatani at CCFE. So I guess the main question is, why do we even care about turbulent transport in the diverter? Well, to put it simply, there's a lot of power in kind of fusion reactors, and when they hit plasma-facing components, they can cause all sorts of damage. A general rule of thumb is we want to keep the power load below about 10 megawatts per meter squared, and a few mitigation schemes have been proposed, such as detachment and SuperX. So the kind of geometries I'm looking at kind of focus in this yellow region here, the diverter region of a tokamak. And basically, this is the exhaust where power leaving the core travels through the scraper layer and hits the target plates at the end of the diverter. And I'd like to try to look at ways of spreading the power load. So what does spreading the power load mean? Well, it's kind of looking at these kind of heat profiles here, which is basically well described by convolution of an exponential decay in the outer scraper layer to the right of the separatrix, and also this power spreading factor S on the left-hand side of the separatrix. So this convolution gives us this thing called an I function. The main things I care about is the power spread into the PFR, which again is the left-hand side of the separatrix, and the scraper layer width, which gives the width on the right-hand side. Flux expansion also plays a role, but I'll mainly focus on the power spread into the PFR for my PhD. So the main figure of merit is the overall heat flux channel width, given by this figure, this integral power decay length here. And I want to look at the effect of turbulent transport on kind of widening these profiles in the different geometries present. So one of those geometries is the SuperX, and its kind of trademark feature is dragging the plasma out to larger major radius. This has two main effects. It increases the connection length, the distance the plasma is from upstream to the target plates, and it also promotes flux expansion to increase the plasma wetted area. So the flux expansion can be seen here, where you see a flux tube is kind of expanded by the time it reaches the target plates. It's also expanded in the colloidal direction, but the main thing is the connection length is also increased as you go into larger major radius, and this gives the plasma more time to cool down. And these effects kind of play well into a phenomenon known as detachment, and this is where the plasma essentially kind of extinguishes just before it reaches the target plates, and this is good for reducing, the plasma power load onto the target plates. And kind of the main effects are to do with plasma neutral interactions. So there are quite a few plasma neutral interactions here, but the main things to consider is the impurity radiation loss and kind of the full volumetric recombination. And the main uptake of all this is that plasma coming from upstream is really hot, but by the time it gets to the target, it's very cold, and you have a lot of sinks in the process. So have we seen this? Well, yes, it's been observed in many places. This example in TCV, where we kind of see this rollover, where despite the upstream density increasing, the overall flux to the target plates decreases kind of counterintuitively because of all those neutral effects. And we see it's quite sensitive to different aspects of the diverse geometry. So why do we care about turbulence? Well, turbulence is kind of the main mechanism for cross-floor transport in tokamaks. And I'd like to see how the turbulence is changed when you go into these SuperX configurations and when the detachment kicks in. So how exactly am I going to investigate this? Well, I need a model that includes geometric effects, can actually efficiently model turbulence, which is quite a computation extensive process, and also accounts for the somewhat complicated plasma neutral interactions. Well, who can help? Well, of course, it's Hermes. So here's an example of a sim that I do. You can kind of see this radiated power if you focus on the image on the right, where you can kind of see this radiation region slowly spreading out from the strike point in the radial direction, and also kind of going further upstream, which is what you kind of observe in real life. So kind of the real life sims that I'm looking at are these TCV cases. So there you saw the horizontal leg, but I'm also running sims in this vertical leg configuration. So this is kind of the SuperX version, and I'm trying to compare the kind of transport effects in these two cases. So one of my first preliminary results is this kind of looking at rollover, where I'm seeing that the actual point of rollover isn't changed between the horizontal and vertical leg configurations, but the overall target flux is quite reduced, at least while still in the attached regime for the horizontal leg. And this is kind of expected because of the increased connection length. So I also do some 3D sims because Hermes allows that. I start with slab simulations because these simulations are quite computationally unstable. And the end goal is to kind of have the saturated regime, but in a full geometry thing. And what am I trying to learn from these? Well, some of my previous work looks into this thing called private flux region filaments. So this was noticed in MAST. So here we have kind of 3 main groups of filament in the private flux region scope layer, and I'd like to use a fast camera to kind of complement my simulation work to kind of compare the two. So here's some kind of crude initial fast camera measurements that was taken at TCV. So here's like the central column, it's another single null configuration, and the inside is kind of the private flux region, where even using kind of an outdated fast cam, you can kind of track these filaments. But yeah, so kind of the main takeaway from my project is that I'm looking at power load mitigation and seeing how diverted transport can be helpful for that process. I'm using Hermes 2, and I'd like to compare my simulation work with Hermes with some fast cam measurements at TCV. Thank you all for listening.
Thank you very much, Hasan. That was a great talk.